Hello everyone, I am Ercan Ertekin from Ankara University. Um, Today I would like to present our last results for a three-phase 100 kilovolt amp transformer with fault current limiter function. And uh, yes, my speech outline is first fundamentals and previous work, and three-phase 100 kilovolt amp transformer with FCL function, and the conclusion. Um, Current limiting by superconducting fault current limiter is an important application for superconductors, and we can we need to improve our knowledge and application experience for this. Uh, we used for this transformer we used magnetic flux transfer for with YIPCO loop, superconducting loop. This is an innovative work for us because we can use magnetic flux transfer to operate this transformer. We have primary winding and secondary winding as a conventional winding. It can be copper or aluminum. Then we used superconducting loop for connection of these two independent iron cores. For this, what is the key feature here? It is easy, and basically the net magnetic flux inside the superconducting loop should be zero when it is a superconductor, and we use this feature. And as a previous work in the laboratory, we made a three-phase 6 kilovolt amp transformer for this application, and it is published in 2000. It was published in 2017, and as you see here, there is no electrical connectivity with these iron cores. There are only three superconducting loops here. And yes, it worked as a FCL, and also if there is a fault on one of the phases, the others one are working properly. And the FCL property we can see here from the previous work. Here there is this is the starting point of short circuit, and this is the secondary current in the secondary side of the transformer, and it is reducing. And after this experience, we started a new project as titled Distribution Transformer with FCL Specialized here about years ago, and we upgrade the design. What is the difference I want to show here? This is a conventional transformer. This is primary side and this is secondary side, and there is no superconductor here. These are the conventional, and this is before. This is the normal working condition, and this is the short circuit. And then we added to the middle another leg, and we added also here superconductor for FCL function. When we compare the here, when we compare the magnitude of the total magnetic flux density, they are almost the same here. But the difference is here, this is after the quench. So after the quench, the superconductor is not a superconductor, and the magnetic flux is flowing through this block. And the secondary side, as you see, there is a very, very few magnetic flux density. For this design, we also introduced a new former for superconductors. Why we need this? Why we need to do this? Because as you see from the table graphic, you can see here, when we don't use a former for this action, the heating is growing up to about 300 K. And if we use a former like aluminum or copper, the heating is limited from here, about here. This is important for protection of the superconductor. And we introduced this former for superconducting winding. Also, I forgot to say, also to prevent further mechanical problems, also during the fall condition, the former was made with vertical grooves here. Yeah. And the cooling system of this transformer is made from GFRP. And we have a vacuum jacket here and MLI also in the cryostat. We use this system, LN2 inlets, spray port, vacuum port, former, and we can see the vacuum volume here. The advantage of this cryostat, we don't need any current lead for electrical connection here, because this is a closed loop. This is an advantage for cooling volume for us. And the parameters of the superconductors we used for each phase 30 turns, and the total length of the superconducting tape is about 100 meters, and the other parameters can be seen here. And the simulations results we have and we introduce here. This is the secondary side of the transformer and the current values. As you see, if we don't use superconductor, the peak of the current is about 400, above the 400, and if we use a superconducting loop, it is reducing about 300. So for three phase, we see here the current limiting here. These are the simulation results without superconductor, and these are the three phase of the transformer with superconducting loop, and the nominal current values is here. For this system, we find a center for this test, short circuit test center in Istanbul. They can only normally make durability test of the transformers, but they also made these tests for us. And as you see, this is the real test. in the laboratory in the center, and we can see here the limited current. But we applied the low voltage, about 401 volt, from the secondary side, and primary was open. And then at the time of this 1.71 second, short circuit started and primary to the primary during the 145 milliseconds, and we get these results. If we compare about the previous one here, the limited current and the tested short circuit test values are compatible. And this is the another test. This is from the input voltage applied from the primary side and secondary is shorted. Then we got these values, and they are almost the same. And we added because the protection of the superconductor is very important issue for applications, and the 77K is a little bit risky because of the quench, and there are a lot of evaporation on the liquid nitrogen. So we wanted to add subcooled nitrogen cooling system to our transformer. How did we do it? We used a heat exchanger here, as you see, and it is about at 65K at 17 kilopascal. So this is an advantage for the application. What is the advantage? During default, at 65K, the evaporated liquid nitrogen will be less, while the liquid nitrogen temperature decrease, the JC of the superconductor will be increased. This is another advantage of this system. And first, we tested the heat exchanger in the laboratory with a turbomolecular pump. Normally, we need a root pump for these long-term usage, but we don't have in the laboratory, and we used the first turbomolecular pump, then the rotary pump in parallel, and we had some results. What are they? Yes, the first results here for heat exchanger, it is starting from 77K and getting lower to the 64 Kelvin. For long-term usage, we need root pump for this. The second test was made on the transformer. Here are this is the green one is the heat exchanger temperature. The blue one is the cryostat 1, and the red one is the cryostat 2. And this is another test, but with the rotary pump, it is not very long-term test, so we see only these small changes here. And this is our system. 3 independent iron core, 3 cryostat, 1 heat exchanger, and the diode. Yeah. As a conclusion, we produced during this project a three-phase 100 kilovolt amp transformer with FCL function is produced, and subcooled nitrogen cooling system integrated to the transformer. And this transformer can be used for private systems to prevent them from the possible damages during a fault. And initial costs are low especially because of the closed loop. There is no current lead and the other electronical connections. And to protect the superconductor from the heat flow during a quench, a former has been introduced for this work. Thank you for your attention.
Did you experience any destroy of superconducting wirings during quench process?
Yes, we tested. For transformer, we didn't.
Transformer.
No, we didn't test it. We only test the superconductor separately. For the transformer, we only tested short circuit, and it is quenched, but there is no damage.
So quenching did not damage?
Yeah.
The superconductor.
Uh-huh.
Okay. I have another question actually.
Yes.
If you used a superconductor with higher critical current density, how would you reach the FCL property? Would it be a larger fault current or would it be smaller fault current?
It is up to the place where you want to use this transformer. If you need low voltage system or high voltage system, yes, superconductor needs to have large JC.
Okay, thank you.
I have a very naive question. Transformer steel is saturated at 2 Tesla. Does it mean that you use just low currents?
Again, please.
The transformer steel saturates at 2 Tesla. After that, transformer does not work.
System.
Yeah.
Yeah, we are using also saturation, but a bit different from the saturated core FCLs. It is a bit different.
Yeah.
Because for saturated core, additionally DC current applying, but we don't use it.
Okay, but what are the range of the currents you use?
Range.
Yeah. The limit.
Limit for this limit it is about 150 amp.
Uh-huh.
Yeah, we used.
Uh-huh.
After
Okay.
this, we can see quench.
Okay. So this is really low current. Thank you.
But it can be arrangeable.
Okay.